Dear student, in this video, we discuss about the boundary layer theory. You know very well that the boundary layer theory, if Reynolds number is small, then the viscous forces will be predominant and effect of the viscosity will be felt in the whole flow field. And if Reynolds number is large, then the inertial forces will be predominant, and in such a case, the effect of viscosity can be considered to be the confined in a thin layer which is known as boundary layer adjacent to a solid boundary. So the Prandtl boundary layer theory. In 1904, Prandtl theory divided the motion of a fluid around the object into the domain. A thin domain very close to the object where the viscous forces are predominant. In outer domain where the viscous forces may be neglected in the domain, the fluid is treated as non-viscous fluid. The first domain is known as boundary layer and the second one of known is as external boundary. So the principle of boundary layer is the effect of viscosity is apparent only in a thin film around the boundary of any object, the rest of the fluid being treated as non-viscous. And the pressure distribution in non-viscous fluid are known as this shows this diagram. So the boundary layer equation. So the consider two-dimensional motion of incompressible fluid of small viscosity. Take x-axis along the surface of the wall and y-axis are normal to the surface. So the equation of continuity is del u by del x plus del v by del y is equal to 0. This is our equation number 1. And the nearest talk of equation of motion in absence of external forces are delta u by delta t plus u del u by del x plus v del u by del y is equal to minus 1 upon rho delta v by delta x plus nu del square u by del x square plus del square u by del y square. Let delta be the thickness of the boundary layer and guided velocity q and the main stream with the velocity u. Then the velocity u changes from u to u in the main stream in a length of it implies that 0 is less than equal to y is less than equal to delta, and at y is equal to 0 u and v are equal to 0 as velocity vanishing on the surface of the solid, and u is equal to capital V is equal to at y is equal to d. So the v is equal to 0, u and small v is equal to 0, and when y is equal to delta thickness of the boundary layer, then u is equal to capital U. Let us denote order of u by order of u. Assume your 0 is less than y, y is less than delta, then del u by del y is large as its order is 1 by delta, and soon order of del square u by del y square is equal to 1 upon delta square, and order of delta v by delta y is equal to 1, and order of del u by del x is equal to 1. But when y is equal to 0 and v is 0, then order of v is equal to 0, then the order of del square v by del x square is 1 upon. So finally u delta u by delta t, del u by del x, del square u by del x square all are of order 1, and v delta v by delta t, delta v by delta x, and del square v by del x square are of order of delta, and order of delta u by delta y is equal to 1 upon delta, and order of del square u by del y square is equal to 1 upon delta square, and order of delta u upon delta y into 1, and order of del square is equal to 1 upon delta. So but delta is a small number, so 1 upon delta is a large number. So in equation 2, del square u by del x square is negative as compared with del square u by del y square. So our equation become del u by del t plus u del u by del x plus v del u by del y is equal to minus 1 upon rho delta p by delta x plus v del square u by del square. By the order of viscous term is the same as the order of initial term. So then we get, so this result gives the estimate of thickness of boundary layer. Now consider the equation 3 and equation 2. Every number of left hand side of order delta y in equation 3. So it means that the term of the equation 3 are of order smaller than those in equation of 2. So all term in the equation 3 are order of delta. So they are negligible. Then from equation 3 become minus 1 upon rho delta p by delta y is equal to 0. So the finally differential equation of a boundary layer are del u by del x plus del u by del y is equal to 0, and delta u by delta t plus u delta u by delta x plus v delta u by delta y is equal to minus 1 upon rho delta p by delta x plus v del square u by del y square, and delta p by delta y is equal to 0. So the equation 4 are known as Prandtl boundary layer equation with the boundary condition u and v is equal to 0 when y is equal to 0, and when y tends to infinity is equal to capital U, which is the function of x and t. So the Bernoulli's equation for steady motion is applicable. Either the mean stream is equal to 1 upon rho delta p by dp by dx plus 1 by 2 twice dv by dx. So our equation 4 become del u by del x plus del v by del y is equal to 0, and del u by del t plus u del u by del x plus v del u del y is equal to u del u by dx plus v del square u by del square. This is our equation number 5. This equation is known as Prandtl boundary layer equation, and it's used in many research problems. Thank you.